Swayam Prabha. Digital India. Educated India.
The next set of motors that we are looking at, or next set of engines that we will look at, is liquid rocket engines. Okay. Now, just like we had certain classifications of solid rocket motors depending on whether it is a double base propellant or a homogeneous propellant, we also can categorize the liquid rocket engines into monopropellant, Now, a monopropellant system is one wherein the propellant decomposes, okay, in an exothermic fashion, and then the energy is released. Okay. Whereas in a bipropellant system you have fuel and oxidizer which mix and burn, and then you get the high pressure, high temperature. Fine. We will discuss this a little more in detail, but firstly the bipropellant systems are themselves further classified as hypergolic, non-hypergolic, earth storable, cryogenic, and pump fed and now what do we mean by hypergolic and non-hypergolic? Hypergolic systems are those wherein if you introduce the liquids, as soon as they come in contact with each other the reactions take place. They do not need any source of ignition. Okay. Whereas a non-hypergolic system you need some ignition energy to initiate the reactions. This does not need any ignition. And earth storable and cryogenic, the earth storable systems are those wherein the propellants can be stored under ambient conditions of pressure and temperature. Whereas if you look at cryogenic engines, they use typically hydrogen and oxygen, or kerosene and oxygen. Kerosene and oxygen is a semi cryogenic system because kerosene is in some sense earth storable, and oxygen, liquid oxygen, if you use that is a cryogenic fluid. Cryogenic essentially means that these are gases at ambient conditions of pressure and temperature, and you need to cool them in order to ensure that they become liquids. Why do we need to have liquids? primarily because the density of liquids is much more than the density of gases, and if you store them as liquids, then you can store them in a smaller volume. Gases, you can argue this way, that you can pressurize them and increase their density, right. That is one of the other routes, but when you pressurize them, we will see that the thickness of the pressure vessel keeps on increasing depending on the pressure. So, and therefore, it does not become useful after some time to store them as gases at high pressure. Okay. So, therefore, it is seen that if you go to liquids, then it is a lot better. So, cryogenic liquids typically are liquid oxygen and liquid hydrogen systems. Okay. And last is pump fed or pressure fed. Liquids, when you store them in certain tanks, okay, they need to be pumped in or fed into the engine. Now, how do you do it is what determines this classification. If you have a turbo pump fed system, okay, then it is called as a pump fed system, and if you just pressurize the tank and let the liquid come out at high pressure, that is called as a pressure fed system. Usually pressure fed systems are low thrust devices, whereas turbo pump fed systems are very high thrust devices. We will discuss them a little more in detail. Firstly, starting with the monopropellant thruster. Now, if you look at this figure, this is the typical monopropellant thrust system. You have an inert gas bottle that pressurizes the liquid here. Why do we need to use inert gas? It is because you do not want reactions to take place inside the tanks itself, right. You want the reactions to take place where you have the thrust chamber. So, you pressurize it with an inert gas, either helium or nitrogen. Helium is, if you use it, it is very obvious that helium has a lower molecular weight. So, even if you have a very large tank, then the molecular weight being low for helium, the weight of the gas in this tank will be lower. But unfortunately, if you want to store them for a longer time, right, because this is very low molecular weight, it is usually seen that it tends to leak over time, and you cannot store it for very long times, and therefore people also use nitrogen as a pressurant. Okay. Nitrogen, you can store it for a much longer time. Then you have a pressure regulator which regulates the downstream pressure. The pressure in the inert gas bottle is typically of the order of 350 bar. Okay. So, 350 bar, you come down to something like 25 or 35 bar, and then you have this liquid monopropellant tank. You have a diaphragm here, right. That is basically to ensure that most of this monopropellant systems are operated in space or under very low gravity conditions. Now, under normal gravity conditions, you will always find that the liquid will be at the bottom. So, therefore, if you have gas that is pressurizing, it will expel it out, but there is no guarantee of that happening in very low gravity conditions. So, therefore, you need a diaphragm so as to make sure that the pressurant is on this side. Okay. Otherwise, the situation could be inverted too, and you would end up pushing in inert gases only. Then you have the liquid monopropellant here. There are two liquid monopropellants that are typically used. One is hydrazine or N2H4. The other is hydrogen peroxide or H2O2. Okay. Both of these are unstable compounds, and if you see here, this hydrazine breaks up into ammonia and hydrogen and nitrogen, and this breaks up into water, oxygen and hydrogen. So this is the monopropellant tank, and after this there is a there are thrusters, small thrusters, a cluster of them. These are typically used in satellite systems for station keeping applications, okay, wherein you need very low thrust. Now there are solenoid valves attached here. Solenoid valves are typically off, and if you give them a particular voltage and current, they turn on, so they can be remotely operated, okay, and it then feeds into what is seen here as a thruster. If you compare this with a solid rocket motor, the propellants and the thrust chamber were identical. I mean, there was no other thing, right? They were both stored in the same place, and which is why we said that the specific impulse of a solid rocket motor would be lower, because you need to have compatibility between fuel and oxidizer. So you are not free to choose the best oxidizer and the best fuel, whereas in a liquid rocket motor you have this freedom of choosing the best oxidizer and the best fuel. So therefore you need to have storage and thrust chamber separate. This portion above the thruster is known as the feed system or the storage tanks, and this is the thruster here. Now in this thruster there is something known as a catalytic bed. A typically used catalyst is aluminum pellets, coated with iridium, and because of this catalyst the decomposition of either hydrazine or hydrogen peroxide takes place, okay, and if you look at hydrazine decomposition, that is N2H4, it can decompose into alpha D NH3 1 minus alpha D by 2 N2 . Here if you decompose it completely to nitrogen and hydrogen, okay, you will not get a very high temperature. Typically the T adiabatic, if it completely decomposes, is something like 867 Kelvin, okay, but you won't want that kind of low temperatures. So what is done is there is an optimal value, that is if this alpha D is somewhere around 4 by 3, right, then the temperatures T adiabatic corresponding to this would be 1650 Kelvin, and ISPs would be something like okay. As you can see here, this has a lower ISP compared to solids, but these are used, as I said, in satellite applications primarily because you do not want a continuous operation, you want a pulsed operation, right, and liquids are very convenient for such an application, and therefore although it is of a lower ISP, you tend to use this. The typical thrust that these thrusters will have to deliver is, thrust varies from 0.1 Newton to something like 20 Newton. It is very small primarily because if you look at the application where it is supposed to be used, it is in space, so there is no or the pressure there is very low, right, there is no sensible atmosphere, and correspondingly there is very little drag. So if you give it a very large thrust, you typically want it to be corrected by small magnitudes. If you give it a very large thrust, it could move very far away from the stated position. So therefore you tend to have very small corrections that are made so as to make sure that it goes to the position that it has to be in. And these thrusters will have to be operated typically around undergo a few million cycles that is, they are switched on and off, and the burn time is typically very small. So there, if you look at the thrust time curve for them, it will be like okay, they are switched on and switched off after a certain time, okay, they are not in continuous operation. And if you look at the life of the satellite, right, the one that determines how long the satellite will stay is how much propellant you can carry, okay, and in some sense if you can have a higher specific impulse for this, then you will find that the satellite can be kept in position for a much longer time, okay, which is why people are now looking at plasma thrusters and other electrical thrusters. The good thing about these electrical thrusters is they have very low thrust, which is what is needed for this operation, but their ISPs are typically 2 orders of magnitude more than what is seen here. So therefore your operation time will increase if you have a higher ISP. So that is the direction in which people are moving. Now let us move on from the monopropellant thrusters to bipropellant systems. Let us first look at this pump fed and pressure fed systems. This here figure here shows a bipropellant pressure fed system. You will have inert gas bottles and then the pressure regulator. As I said, you have both nitrogen and helium, and then you have a separate oxidizer and fuel tank, okay. And if you look at the pressure downstream of this gas bottle, in the tanks it is somewhere around 30 to 40, and in the combustion chamber it comes down to something like 20 to 30. So these are basically fed by because of the high pressure here, okay. and then you have the combustion chamber and then the nozzle. As opposed to this, if you remember, if you add heat at the highest pressure, right, then you can extract more work out of that system. So therefore, if you want larger thrust, if you remember, the thrust equation is nothing but Cf Pc AT. So if you have a very low pressure, then the thrust will also be lower, and if you have a very high pressure, your thrust can be much more larger. So that is the idea behind pump fed system, and the schematic of that is shown here. What you see is again pressure bottles, but these pressure bottles are much smaller in size, and what happens here is you don't pressurize it to something like 30 or 40 bar, you pressurize it to something like 3 to 6 bar, which is higher than the vapor pressure. Why that is so, we will discuss a little later in the course, okay. And therefore the tanks are essentially maintained at low pressures, they are not at high pressures, they are not at 20 bar or 30 bar, right, they are at very low pressures. So therefore the thickness of the tank material can be smaller, and then you have turbo pumps here, okay. You have a separate pump for fuel and separate pump for oxidizer, and then you have if you have to run these pumps, you need a turbine, right. So this turbine uses a part of this fuel and oxidizer system, okay. Part of this feed is given to the gas generator indicated by G here, the pumps are indicated by P, and the turbine is indicated by T. Now if you remember what you studied earlier in an earlier course, that is on gas turbine engines, you will see that the turbine inlet temperature needs to be smaller, okay. They cannot be very high, although here in the combustion chamber of the rocket motor you can go up to 3300, there it is restricted to something like 1600 to 1800 Kelvin. So here in the gas generator you need to be careful so as to ensure that the temperatures do not exceed that, and then you have a turbine which essentially powers the two pumps, okay. And if you have to start it initially, right, initially if you have to start the system, you need a small propellant charge, typically a solid propellant is used to provide this, and that will first run the turbine, right. If the pumps are not run, then you do not have anything coming into the gas generator. So initially to run the turbine, a small solid propellant system is used, and then the turbines are turned on, and then the pumps become operational and they start feeding in the propellant, and the gas generator can then be used to run the turbine. And then you have in the combustion chamber here, you can go to something like 50 to 200 bar, okay. The combustion chamber pressures are very high here. In space shuttle, the combustion chamber pressure in the space shuttle main engine, liquid engine, is somewhere around 200 bar. So somewhere in the pipeline you will have pressures exceeding 300 bar, very high pressure systems. If you have a high pressure system, the other advantage is that your size of the thrust chamber, right, the size of this rocket motor can be very small, and as I said, if you want a very large thrust, thrust is dependent on Pc, right. So if you have a very high chamber pressure, then you can get a very high thrust. So this also in some sense needs a lot more cooling because of the high heat that is generated here, and typically part of the fuel is pumped through a regenerative jacket, okay. There is a jacket around the nozzle as well as the thrust chamber, okay, and typically liquids are pumped through this, and these liquids take in the heat and then this is used up again in the combustion chamber. So in a sense, what we had discussed when we discussed nozzles, right, we said there is a loss because there is a loss of heat to the ambient. That is minimized if you have regenerative cooling, because you are essentially using what has been lost to the walls again is recirculated back. Okay. And this, as I said, is going to give you very high thrust. It is important to note this, that if you want to decide on what system to use for a particular application, remember we said the satellites, because it is a low thrust system, we wanted to use monopropellant systems. When do we use a bipropellant system? When do we use a pressure fed? When do we use turbo pump fed? Now what is shown here in this plot is, you have on the x axis total impulse. Total impulse is nothing but F into operational time, okay, or T burn. So either if you have a very large thrust, or if you want to have the operation for a very long time, right, then your impulse becomes larger. Now if you see, this is x axis is total impulse and y axis is system weight. Okay. If you see this, if you can use cold gas for certain applications, that is when the impulse requirement is very small, then this becomes a very good system, right. If you have impulse requirement of the order of 10 power minus 1, there is no point in using a bipropellant system. Bipropellant system will in fact have a very heavy weight, because you need to have pumps, you need to have all kinds of devices. So it is better to have cold gas if you are using it for a very small impulse. And then further, this curve, the monopropellant system comes in, that is, if your impulse is up to 10 power 1, it is better to use a monopropellant device, and then a pressure fed bipropellant device, and then lastly turbo pump fed bipropellant system. Now the difference between bipropellant pressure fed system and turbo pump fed system is essentially because of the tank weight. If you notice in the earlier figures, in the pressure fed system, the gas bottle is the one that is pressurizing it. So it needs to have a very large volume in order to fill the entire tank volume. So if your thrust is large and as well as burn time is large, then you are going to have a lot of liquid in the tank. So the tank needs to be filled at something like 30 to 40 bar. So the inert gas bottle weight goes up as well as the tank weight goes up, okay, because if you remember from your structures, it is PD by 2T, right. So the thickness goes up as the pressure goes up. So therefore the system weight is going to increase, and that is why you will find that beyond a certain fraction of the impulse, if you use a pressure fed system, then it will not be very beneficial. Its system weight is much higher than compared to something like a pump fed system. If you have something like 10 power 5, you can see that the system weight will be something like 10,000 kgs. If you use turbo pump fed system, but whereas if you use a pressure fed system, it will probably be something like 10 power 7 or 10 power 8, okay. So in a sense, this graph gives you an indication of what is to be used if as per your requirement. So the essential thing to note is, you need to know what is your impulse. If you know the thrust time curve, you can calculate the impulse, and therefore you can choose the appropriate system. We will stop here, and in the next class we will look at little more in detail on the liquid propellant systems. Okay, thank you.